Welcome to the video on entropy changes and expansion, phase transitions, and heating. So entropy changes upon expansion. Recall that the entropy change of an ideal gas expanding isothermally has this equation here, where the change in entropy is equal to n the number of moles times r the gas constant times the natural log of the final volume divided by the initial volume. So because entropy is a state function, the change in entropy of the whole system is independent of the path. But the total entropy change of the universe, meaning the system plus the surroundings, is dependent upon the path because it depends on how much energy is released from the system to the surroundings as heat. So, for any process, the energy lost as heat from the system is gained by the surroundings. So, the dq, the change in some infinitesimal change in heat for the surroundings, absorbed by the surroundings, is equal to the opposite of the energy absorbed by the system. Where here, we're leaving off the subscript sys or system from this q. And so for a reversible change, then for some measurable change delta S for the surroundings, the change in entropy of the surroundings is equal to the heat absorbed by the surroundings, which is equal to the opposite of the heat absorbed by the system reversibly divided by the temperature, which is equal to minus nr times the natural log of the ratio of the volumes. And so the total energy change is therefore has this equation. So the total entropy change, delta S total, is equal to the entropy change for the system, delta S sys, plus the entropy change for the surroundings, delta S surroundings. And so now we can combine together the entropy change for the system, which we saw a couple of slides ago, plus the entropy change for the surroundings, which was negative, that same value. So when these two values add together, we get a value of 0. So the total entropy change is 0 for a reversible process, only a reversible process. But for isothermal free expansion, the work done is 0. And the internal energy change, delta U, is equal to 0. And we also know that delta U is equal to Q plus W. So if the internal energy change must be 0, because it's isothermal free expansion, we know that the energy of our system doesn't change. And if the work done is 0, because it's free expansion, it's not being opposed, that means that the heat absorbed by the system, or released, must be 0. So Q is 0. So if Q is 0, then the entropy change for the surroundings must be 0, because remember the entropy change for the surroundings is equal to the heat absorbed by the surroundings divided by the temperature of the surroundings. So if the heat absorbed by the surroundings is 0, then the entropy change for the surroundings is 0. The surroundings aren't gaining any energy. And that means that the total entropy change of the universe, which is still equal to the entropy change for the system plus the entropy change for the surroundings, that has to be equal to n times r, the gas constant, times the natural log of the ratio between the volumes, the final volume to initial volume, plus, now we know the entropy change for the surroundings is 0, so we plug in a 0 there, and that means that the entropy change for isothermal free expansion is nr natural log of Vf over Vi. Right? So here, the entropy change is not 0. Thus, the total entropy change for an irreversible process is not 0, it's greater than 0. It has to be greater than 0. Now let's look at phase changes. So when a solid melts to a liquid, right, we have this process occurring. We have a solid here, and when the solid turns into a liquid, right, the substance is transitioning from a very highly ordered state where each of the atoms is in a specific place within the crystal to a moderately disordered state. Right? All of the molecules are together here at the bottom of the container. It's not as disordered as the gas is, but the molecules are no longer in very highly ordered states. They can move about, they can move past each other, and so it's in a moderately disordered state. Thus, in going from this highly ordered state in the solid crystal to the moderately disordered state, the entropy should increase. When a liquid boils to a gas, so this process here, the substance transitions from a moderately disordered state of the liquid to a very highly disordered state with the gas. Right? In a gas, all the molecules are acting totally independently. None of them are together. There's basically no structure left at all. There's no order left. The molecules are just distributed randomly in the container. They're moving at random speeds, and therefore the entropy should increase as we go from a liquid to a gas. All right. So let's consider a system that's at its normal transition temperature. T transition, this T transition here. The temperature at which two phases of matter are in equilibrium. So this might be the melting point or the boiling point at some temperature. And so the normal transition temperature for ice in equilibrium with liquid water is 273 K, or 0 Celsius. The normal transition temperature for liquid water in equilibrium with steam is 373 Kelvin, 100 degrees C. And at the transition temperature, any transfer of energy as heat between the system and the surroundings is reversible because the two phases in the system are in equilibrium. So if we have, let's say, ice and liquid water in equilibrium at 273 K, if we have a transfer of energy as heat from the surroundings to the system, so we are absorbing energy into the system, the temperature isn't going to change. The temperature of the system doesn't change. Instead, we're changing the ratio of liquid water to ice. Right? As we absorb energy, some of the ice melts, and we get more liquid water, until the point at which we get 100% liquid water, and now we no longer have ice and liquid water in equilibrium, and so then this is different. All right. So recall that at constant pressure, we have an equation here. At constant pressure, the heat absorbed, Q, is equal to the enthalpy change for that transition, delta transition H, delta TRS H. And thus, the change in molar entropy for the system is this equation here. The delta S is equal to, remember, we know that the entropy change is equal to Q divided by the temperature. So at some transition temperature, TRS, and then we know that we can substitute in our enthalpy change for Q. All right. And now if the transition is exothermic, then the transition enthalpy will be less than 0. This is the case for freezing or condensing, right? With freezing or condensing, we're releasing energy. We're releasing energy as heat to the surroundings. So if the transition is exothermic, then the entropy change is negative, which makes sense. If we're condensing from a gas to a liquid, we should be decreasing the entropy, right? Our system, if it's going from the very highly disordered state of a gas to a liquid while it's condensing, the liquid is more ordered, so the entropy change is negative. Likewise for freezing, we're going from a moderately disordered liquid state to a very highly ordered solid state, so we're losing entropy. Note that we're losing entropy for the system. In the universe overall, we still have to be increasing the entropy of the universe. So the total entropy of the universe, which means that heat that's leaving our system and going into the surroundings, the entropy of the surroundings is increasing there. So there, the entropy change for the surroundings is positive, as the energy is released to the surroundings as heat, and thus the total entropy change is 0. All right, so here we have a table with some standard entropies and temperatures of various phase transitions for fusion, so the melting process, and for vaporization at the standard boiling point, and so, or freezing point. And you can note that over here, the vaporization values are, a lot of them tend to be near about 85 joules per mole K. So the ones that I have listed here, the water, the enthalpy of vaporization is significantly higher there, and for helium it's significantly less. But those are two pretty different gases. So this value of 85 joules per mole K is kind of a special value, and that's occurring because of the because a roughly comparable change in volume occurs when any liquid vaporizes to become a gas. Now, of course, this depends on the liquid that you have. So something like water, water has a lot of structure to it as a liquid, and so when it vaporizes to become a gas, it's losing even more of that structure. Now, it has a lot of structure because of the hydrogen bonding in the water, so the molecules in water, liquid water, are still fairly highly ordered compared to most other liquids. Now you notice that if I go back, the entropy change for helium is much lower. It's only 19.9 joules per mole K instead of the roughly 85 that most compounds are, and that's because helium is already really quite disordered in the liquid phase. So this observation that the entropy of vaporization for many liquids is close to 85 joules per mole Kelvin is called Truton's rule. So liquids that deviate from Truton's rule again do so because of strong intermolecular interactions that result from a partial ordering of their molecules, like the water. And so when these substances become gases, a larger entropy of vaporization is seen because the partial ordering is overcome, in addition to the normal increase in volume for most other liquids to gases. So looking at the entropy of vaporization for water as opposed to hydrogen sulfide is fairly similar to water, except that it doesn't have the hydrogen bonding that is present in water. And so the hydrogen sulfide has an entropy of vaporization that is pretty close to 85 joules per mole K. All right, so now let's turn to entropy changes when we heat a system. So remember that the entropy change for a system is equal to the integral from the initial state to final state of dq reversible over T, the temperature. And we can use this equation to calculate the entropy of a system at some final temperature Tf if we know the entropy at another temperature Ti, and we know the heat required to change its temperature from one value to the next, from one temperature to the next. And so we have here this equation. So we have the entropy at some final temperature is equal to the entropy at the initial temperature plus this change in entropy. All right. And now we're concerned with the entropy change when the system is subjected to a constant pressure, as from the atmosphere, or if we control it in some other way, during the heating. So we can then use our definition of constant pressure heat capacity, which is this guy. And we can plug that in. So if we replace dq here in our integral, we end up with this integral. And then, if the constant pressure heat capacity Cp is independent of the temperature within the temperature range of interest, which is a reasonable assumption to be making, then we can take that outside the integral. So we can take this Cp outside the integral, as we've done here. Take it outside the integral there. And now we're left with this integral here, which evaluates to the natural log of the final temperature over the initial temperature. And so note that we could separate this as the natural log of the final temperature minus the natural log of the initial temperature, but combining the two together like this makes the units work out well. So now we have a unit of temperature, Kelvin, let's say, divided by another unit of temperature, Kelvin, and that makes this quantity inside the natural log unitless. So that works out better that way. All right, so here we have our equation from the last slide. And on the right side here, we can see the ratio plotted on the bottom here. We have the ratio between the final temperature and the initial temperature. And on the left, we have the entropy change divided by the number of moles N and R. And so you can see here this logarithmic dependence if we pick any one particular value for the heat capacity. So we have, let's say, this value here. So you can see this nice logarithmic dependence of the entropy on the temperature. All right, now, if we actually want to measure the entropy, let's look at how we can go about doing that. So the entropy of a system at some temperature T is related to its entropy at T equals 0, so absolute 0, by measuring its heat capacity, Cp, at different temperatures, and then evaluating this equation that we have. So now, if we're talking about absolute 0, T equals 0, now our assumption that we can pull Cp, the constant pressure heat capacity, out of the integral is starting to break down, because the constant pressure heat capacity is significantly more likely to change as we get close to absolute 0. So if there are phase transitions between absolute 0 and T, the temperature we're looking at, which becomes more and more likely the farther we get away from absolute 0, then we need to account for them using our entropy change for that phase transition that we've derived earlier. And for a substance that melts at TF, TF being F for freezing, and boils at TB, B for boiling, the molar entropy is given by this equation, which is really long. It's both lines all here. So the molar entropy at temperature T is equal to the molar entropy at temperature 0, which we don't know what it is, plus the entropy change from temperature 0 up to the freezing point at using our constant pressure molar heat capacity there, plus now our enthalpy change for the melting process, the fusion process, divided by the temperature at the freezing point at whatever pressure we're at, plus the integral from the freezing point up to the boiling point, assuming that we're going up past the boiling point. So now we have this integral where now we have the constant pressure molar heat capacity of the liquid. Up here, this S was for the solid at whatever temperature we're interested in, divided by the temperature, dt, plus now our enthalpy of vaporization, divided by the temperature that the substance boils at, plus one final integral from the boiling point TB up to the temperature T that we're looking at. Again, evaluated using the constant pressure molar heat capacity. Now here G means the gas at the temperature that we're looking at divided by the temperature that we're looking at, dt. Right? So that's a giant integral, or rather it's a giant equation with 3 different integrals in it. And so again, up here I have that equation all on one line. So every quantity in that equation can be measured calorimetrically using a calorimeter, except for the molar entropy at absolute zero. Right? But all of the other values we can measure. So really, if we want to look at the entropy at some temperature T, we can compare that against the molar entropy at absolute zero. Now we don't know what that value is, but we're looking at a delta S, basically, a change in entropy from our initial value. And so we have a plot of this to the right. So we have our entropies increasing, and then we have these changes here at our transition temperatures. So at freezing, so we have our entropies increasing as we increase the temperature. Then we get to the freezing point, and now we have a jump in entropy, and that occurs because now we have a phase transition from the highly ordered solid to the liquid. But note that going from the solid to the liquid, we're not changing the temperature any. And then we have an increase in entropy again, only now then we get over here to the boiling point, and we have another big jump in entropy, and then the entropy increases as we increase the temperature from there, and we increase the disorder. So we have on the bottom curve here, this gray portion, that's the entropy. And the top curve, that area is the area under the curve is the total entropy. And this Cp over T temperature, that's the area, the Cp is this curve, the top curve. And we need the integral of the constant pressure heat capacity, Cp over T. Right? So that's the integral that we need for this equation here is the integral, the area underneath this top curve. That's the yellow area there. All right, so one of the problems with measuring entropy is that it's difficult to measure the heat capacity of our substance, the constant pressure heat capacity, near absolute zero, near T equals 0. So we can use this what's called a Debye approximation, the Debye extrapolation, which shows that the heat capacity is proportional to the temperature cubed when the temperature is low. Right? It only works when the temperature is low. So if I go back and show you, here's the Debye approximation, right? And as the temperature gets lower and lower, as we get closer and closer to the origin here, the Debye approximation, the Debye extrapolation, becomes closer and closer to the value here, right? For Cp over T. So it gets better and better, but it fails at high temperature. All right, so that was the entropy changes and expansion, phase transitions, and heating.